Hi, I am Ajay from Sense School.
Hi, I'm Prithvin from Sense School.
Hi, I am Akshay from Sense School. Today we have our project Smart Car Parking System with us for our DLD project. This project counts the cars coming inside and going outside and displays the head count in a display.
We have used 5 volt adapter for the power supply, and we have used 2 toggle switches to use incoming and outgoing cars, and we have used IR sensors, this for entering cars and this for exiting cars, and we have just used a decoder and a counter and AND gate and an NE555 timer IC to generate clock pulses, and a 7 segment display to display the amount of cars. Now I'm going to explain the signal flow in this model. Like if the car enters the parking lot, the entry IR gets triggered and it gives a noisy signal to the NE555 timer IC. So it creates a clean pulse which is sent to the 74HC193 up down counter. These up down counter produces a 4-bit number, and these 4-bit number is sent to the 7447 decoder and produces a decimal equivalent, and this decimal equivalent is sent to the 7 segment display and prints or displays the amount of car in the parking lot. Now we are going to see the working flow of the model. Now enabling the entry IR sensor, it counts the number of car entering the parking lot. After reaching the maximum capacity of the parking lot 9, it goes to the reset state and it closes the parking lot. It detects the number of cars exiting the parking lot. And finally it displays the number of cars in the parking lot. Now I'm going to explain about the internal circuit of the NE555 timer IC, which is an 8-pinned IC which has ground, trigger, output, reset, VCC supply, discharge, threshold and control voltage, and which has a 3 5k ohm resistor which acts as a voltage divider, and a BJT transistor, 2 comparators and SR flip-flop 1, and which is connected to the output driver, which gives a pulse high or low according to the input signal, where we can get the output from the pin 3. Now if the IR sensor is always high, if a car is detected, it gives a noisy signal to the pin 2 of the NE555 timer, which is a trigger pin, which triggers the NE555 timer. NE555 timers one comparator, which the voltage of the comparator which doesn't exceed 1/3 of VCC, and if it doesn't exceed 1/3 of VCC, it gives a clear pulse through flip-flop to the output pin 3. Now if the capacitor inside the comparator it gets charged at initially, and if the voltage at the comparator 2 doesn't exceed 2/3 of VCC, it gives signal to pin 6 threshold, which resets the circuit and gets ready for the next car.
Internal working of IC74HC193N that we have used in our project. It majorly consists of 4 flip-flops and multiple logic gates like AND, OR and NOT to control the logic for counting up and down. So basically these flip-flops can store 1 bit of data, and when a pulse is passed through CPD or CPU, the flip-flops toggle one by one continuously. Now I'm going to explain the pin diagram of 74HC193. 74HC193 is a 16-pin IC. The first the pin 8 and pin 16 are power pins. 16 is connected to 5 volt VCC and 8 is connected to GND, and there are 4 parallel inputs which can be given as inputs to make them which are prefixed values. So the pins are pin 15, pin 1, pin 10 and pin 9. So the when a value is given in these pins, these values are converted to this binary value is taken as the starting of the up or down counting, and we moreover have 2 pins 4 and 5 for counting up and down. 5 is used for 5. Pin 5 CPU is used for up counting, and pin 4 CPD is used for down counting. Pins 3, 2 and 6 and 7 are used for are used as output pins, and pin number 14 is considered as reset pin, and pin number 13 and 12 are respectively carry and borrow pins. When the value exceeds 111 or decimal equivalent 15, it goes to carry output. Then when value goes very less than 0000, which is decimal equivalent to 0, now there's signal in TCU pin number 12, and pin number 11 load PL is used for loading the values into output pins like output pins 2, 3, 6, 7. Now basically how this works is when a pulse is passed through CPU pin number 5, the flip-flops toggle one by one and the count is increased. The flip-flops work in the order 0000, 0010, 0011, 00100. This continues, and when down pin gets a pulse, this is done in reverse process. The flip-flops toggle in a reverse process. So this is how the IC 74HC193N is used for counting in our project.
Okay, now I'm going to be explaining the final stage of the project, which is the decoder and the 7-segment part of the project. The binary output from the counter is not directly readable by humans, so we use a 7447 BCD to 7-segment decoder. 7447 BCD to 7-segment decoder. The decoder takes the 4-bit input and converts it into signals required to drive the 7-segment display. The outputs of the decoder are active low, meaning a segment turns on when the signal is 0. These outputs are connected to the 7-segment display through current limiting resistors. The display then shows the number of cars in decimal form from 0 to 9. So for example, these ABCD pins are the ones which will receive the BCD input from the 74HC193 counter. Now the inputs received from the counter are then converted into these ABCDEFG form, which can be read by the 7-segment. Now for example, let's take the number 6. Now for the number 6 to be displayed on the 7-segment display, the decimal the inputs need to be for the number 6, they need to be 0, 1, 0, 0, 0, 0 and 0. So that means the display will then only display the A part, F, the G, the E, D, C and B. This displays the number 6 on the 7-segment display. Okay, finally the overall system follows this signal flow. The IR first receives the signal from the cars entering the parking system. Then it moves to the 555 timer IC to clean up the received signal. Then the 555 IC sends a signal to the counter, which upcounts the incoming car. Then the counter then sends it to the decoder, which decodes the binary equivalent decoder, and which decodes the binary equivalent, and then finally it's displayed on the 7-segment display.